Yep, thank you. There we go. Okay. Okay, so chapter 2, we're going to be starting to look at alkanes, which are pretty much the simplest organic molecules that we can look at. So we saw in chapter 1 that when we're putting together covalently bonded structures, usually for carbon to be as stable as it can be, carbon wants to have 4 bonds if it's going to have 0 charge in a full octet. And hydrogen wants 1 bond if it's going to have 0 charge in a full duet. So we can pretty much treat these as if they're like atoms in your molecular modeling kit and start clicking these together. So we can do long strings of carbon. So just carbon linked to carbon, linked to carbon, linked to carbon, and so forth. And then to get every carbon the 4 bonds that it wants, we can just start plugging H's in all over everything. So pretty much every carbon in the middle of the chain needs an extra 2 bonds to be happy, so 2 H's, like those 2. And then the ones at the end of the chain need 3 more H's to get their full bond set. Okay, so we're going to be looking at molecules pretty much just like this, just carbons and hydrogens. This one actually happens to be butane, which is a gas at room temperature and pressure, but a liquid when you compress it. So butane lighters are actually full of this stuff. Okay, we already know, though, that carbon can have multiple bonds between carbon atoms. We saw some examples of that. So this actually gives us a basis to subdivide stuff that we're looking at in this chapter. So really, what we're looking at is a subset of hydrocarbons, which are made up of just carbon and hydrogen. like the name implies. But we can sort of break those up into different groups depending on what kinds of bonds you got between them. So they can be either all single bonds, which is going to be called an alkane, or they can have at least one double bond, which is an alkene with an E there. There's only one letter difference between them. Or we can have at least one triple bond, which is an alkyne with a Y. So it turns out these three groups all react very differently from each other in sort of characteristic ways. So we're doing alkanes now. We're going to be doing alkenes a few chapters from now, and then alkynes you'll get to in OChem 2. Okay. So all three of these groups, though, still fall under the same umbrella, which is aliphatic hydrocarbons. And we use that name to distinguish them from the other part of hydrocarbons, which are aromatic hydrocarbons. These if you're taking lab, you have probably already seen some sign of, and maybe from Gen Chem as well. But the pattern here is that almost all of the time that we're going to see for now, they have a ring that's got 6 carbons in it, and they alternate double and single bonds. And then every carbon has one H to give it the full set of 4 bonds. All right, so there's actually a lot more to what makes something aromatic than just this pattern, but for the time being, this will be good enough.
If you have a ring structure that displays double bonds, is it considered an aromatic?
Nope, so it's got to have alternating single and double, otherwise it falls under aliphatic hydrocarbons. So good question. So like this would also include like just carbons with a single bond to each other in a ring. So those are cyclic aliphatic hydrocarbons, but they still react pretty much the same way as aliphatic hydrocarbons. Okay, aromatic are way, way different, and we actually have a couple of chapters dedicated to them and what makes them aromatic and how they react. So that's also an OChem 2 kind of a thing. Okay, so this chapter is just about alkanes for the time being, because they're kind of a good, simple place to start. Okay, any other questions about these categories before I move on? Okay, cool. So we're going to look at a few things in this chapter, and the first thing is how to actually name or describe which molecule that we have from the alkane series. So if the alkane has all the carbon atoms in a continuous line, it's called a normal or an N-alkane. Okay, so the N-alkanes are sort of named after this series that you're going to have to memorize up to number 10 in. So I'm just going to write them all up here. Okay, so number of carbons, name, and structure. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so the first 4 have weird historical origins that are just related to a single molecule that people started studying, and then the name got attached onto sort of the alkane that it's based on. So methane, ethane, propane, and butane. So meth, eth, prop, but are the first four prefixes. And notice that they all end in ane, A-N-E, because they're all alkanes. Okay, after this it's easier because we just go into like Greek counting prefixes. So like if you remember multi-sided shapes, like 5 sides is a pentagon. This is pentane. 6 sides is a hexagon, hexane, heptagon. That's less commonly used, but heptane, octane, nonane, and decane. Okay, so the structures for these, I might do like the first few and then stop because it's kind of time consuming. But you can just show like 1 carbon, 2 carbons, 3 carbons, 4 carbons, and then you just plug in H's until each carbon has 4 bonds. So I'm probably going to get a little short on space here too. Okay, so pretty much you can fill in like that if you want to do the whole series. Okay, so a few things to point out here about this sort of series, and that is, this is the first example we're going to see of a homologous series. So every molecule in this thing varies from the one above it by the addition of 1 extra CH2 unit squeezed into the middle of the chain. And in fact, this CH2 unit that has bonds sticking to something else on either side is common enough that we're actually going to call this a methylene. And you'll note that this actually has the word meth in it, just like methane does. Methane's 1 carbon. This is also 1 carbon, but it's missing some stuff. It's missing a couple H's compared to methane. So we're wedging sort of like methane, missing a couple H's into the middle of the chain every time we go down the table by 1 step. Okay, so usually all the members in a homologous series are going to have behaviors that vary in like a consistent, predictable way. So we're going to look at the end of this chapter, some physical properties for the alkanes and sort of how they relate to the molecular weight and the chain length of the alkane. Okay, so questions about this? Oh, yeah.
Just out of curiosity, the propane that you use in like a grill, is that just an organic? That is an organic?
Yeah, that's exactly this molecule, just 3 carbons and 8 hydrogens. They probably add a little bit more stuff to it because I know, so natural gas is actually mostly methane, some ethane, but those molecules don't smell like anything, and so to help people be able to identify when there's a gas leak, they add like a tiny amount of something that smells really, really bad. So when you smell like sulfur, you can tell, okay, there's a natural gas leak. They might do the same thing to propane tanks that are used for grills, but I'm not totally sure about it, but it's almost all propane. So yeah. Okay. All right, cool. So, so you'll notice that I sort of gave up drawing these halfway down the table, and there's a reason for that. It just gets to be like kind of a tedious pain to draw them out the bigger these molecules get. So what we really need is some more efficient way to draw them that's not just based on the Lewis dot structure. So ways to draw alkanes and other molecules as well. Okay, so we're going to be looking at several different layers of details. The least detailed way that we could do it is just by saying the formula. So the molecular formula. So this is just how many of each type of atom there are. So I'm going to be doing this for butane as my example. Butane is just going to be C4H10. Okay, so that does give us some information about what's in there, but there's actually multiple structures that could have the formula of C4H10. So this happens to be normal butane, but I could also have drawn a structure hypothetically where the carbons were not all linked together in a straight line. So molecular formula gives you some of the picture, but it sure doesn't tell you the whole story. Okay, so I could do all the carbons in a straight line, or I could do like 3 in a line and then 1 coming off the middle. So like that, and then fill in the H's, and that would also have C4H10 as its formula. So I'm going to need a better way to do this. Okay, so just as sort of a side note here, if you do have 2 molecules with the same formula, these are called structural isomers of each other. So same formula, same molecular formula, different connectivity. And not surprisingly, the more atoms you have in a molecule, the more different ways to stick them together there are, and the more structural isomers you're going to see. Okay, so I'm going to take a minute and erase the board here before I move on to another way to do things. Okay. So we need a better way of drawing things that gives us some more information. So the easiest way to do that, or this, I guess the most basic way to do that, is the structural formula. Which is basically just the Lewis dot structure that we saw in chapter 1. So Lewis dot, where we're specifically using the lines between atoms instead of 2 dots. Okay, with a line for each bond. So for butane, that's going to be what I drew up here at the top of the chapter. 4 carbons in a line and a bond to every hydrogen that's attached to each of them. Takes a long time to draw, even for a tiny, simple molecule like butane. Okay. So we need a way to compress or condense this down. So another option that we have is the condensed structural formula. Which is where we can group all of the hydrogen atoms onto a carbon just by listing them after the carbon with a subscript. Okay. So for butane again, we're just going to collapse down the carbon with its 3 H's to a CH3 group. Then CH2, CH2, CH3. And if we want, we can even just take the hyphens out of the middle here and say CH3, CH2, CH2, CH3. Okay, if we want to be even more efficient, we can notice that there's actually 2 repeat units of CH2 in here. So why don't we just use parentheses and group those all together? For butane, it doesn't make that big a difference, but especially for something like decane, where we've got a whole string of methylenes in a row, this will save us some work. So we're going to group like units in parentheses. So for butane, we could do CH3, CH2, 2, CH3. So now it's just as much work to write out butane as it would be to write out, say, decane. Decane would be like CH3, CH2, 8, CH3. So there's still 10 total carbons in decane. Okay. So any questions about those ones? Yeah.
Would that also be like the order that you would draw it in?
For this one?
Yeah, with like the subscripts.
Yeah. So, I mean, you have free choice on like whether to do the H's before or after the carbon. So you could call it like H3C and then like H2C. But you would still do like a CH3 or an H3C at one end and at the other end, and then like the methylenes in the middle. Yeah. Okay. So all of these still involve writing out letters. So there's an even more efficient way to do things that takes a little bit more getting used to than looking at these. So this is actually, this last one, is what we're going to see most heavily in this class. Those of you taking lab have already seen it a little bit. So it's got a few names: skeletal, or line bond, or zigzag. So now we're not even going to write carbon or hydrogen explicitly at all. The rule for this is every bend or end of a line is a carbon. Or in other words, every end of a line segment is assumed to be a carbon. Unless we say something else is at there. By drawing a different atom explicitly. And then we're not drawing the H's either. We're going to assume that every carbon has the right number of H's to give it a full octet, unless we say otherwise, like if there's a positive charge. Again, unless we say otherwise. All right, so carbon's implied by line segments. H's are just implied by not showing anything, really. Any atom other than carbon and H, we have to write explicitly. And we have to show hydrogens on it explicitly. So, by the way, these are called heteroatoms. Those have to be drawn explicitly. Along with their H's. So we can, if we choose, show a carbon or a hydrogen like explicitly by writing it out as a carbon or a hydrogen. Like particularly if we want to draw attention to it for some reason, like it's going to be used for a reaction, but we don't have to. Like it's okay to just show it implied by the structure. Okay, so let's go through some examples. Butane, the one that we've been using so far, is just that. Much faster and easier to write than a bunch of C's and H's. Just to double check, every bend or end of a line is a carbon. So carbon, 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 carbon. I guess one thing I didn't write out here is you can show carbons explicitly like I've just done. But if you do that, you have to show all of their H's. Okay, so I'm going to erase this again because I don't want to draw all the H's and just leave butane as sort of a squiggled line. Okay. So a few more examples here. This aromatic hydrocarbon that I drew up there earlier. This 6-carbon ring with single and double bonds and H's on all of them. Takes a while to draw. Fortunately, I don't have to draw it because that is equivalent to that. I don't have to draw the carbons explicitly unless I want to, and I don't have to draw the H's explicitly. It's just a hexagon with some lines in the middle. Much easier. Another example with some actual like non-carbon and hydrogen atoms in it. If I wanted to say this molecule with one carbon having 3 H's on it and one being double bonded to an oxygen, I can also draw that as this, where I've got carbon is implied to be here with however many H's it needs, carbon is implied to be here with however many H's it needs, and then at this end of the double bond, because it's a different atom, I have to show this explicitly as the oxygen that it is. Question?
For the aromatic hydrocarbon, is there also a version of that you can show using a circle?
There is, yeah. So that's, yeah, we'll get into that later. Yep. So yeah, you might also see this with just a circle because it turns out the distinction between single and double bonds is a little bit more complicated when you're looking at aromatic rings. So, okay, so let's see, one more example. So if I'm doing butane, but with, instead of a CH2 here, maybe it's got a CH where the last spot on this carbon has been filled with, say, a bromine atom. I can do this as butane, like the zigzag structure that I've gotten used to looking at, but with a bromine hanging off of it. And it doesn't really matter if you show it like below or above the zigzag. It's probably easier to just keep it outside of the bend of the line so that it's out of the way a little bit more. If I want to, I can still show like any of the H's on here explicitly. So I could show like the H attached to this carbon if I want to. Or because it turns out to be important for reactions that we'll see later on, maybe I can show like this hydrogen explicitly if it turns out to be something that I want to draw attention to. So I can draw any or all of the hydrogens explicitly, just depending on what I care about in that structure. One thing that is worth pointing out as sort of a warning is that sapling is a little bit weirdly over-particular about this. Sapling sort of tells you if you show one of the hydrogens on a carbon, you got to show all of the hydrogens on a carbon. That's just because the way that their software works. But that's not normally a requirement for showing these structures. A question?
So with the last sentence of like the skeletal description, it's like you can't show carbons explicitly, but you have to show all of the H's as well. Is that basically, is that individually, you can show like individual carbons with explicitly?
Yeah. So if I wanted to, there's a whole bunch of ways I could have drawn this out. Like I could have said this carbon explicitly if I'd shown all the H's on it, or like any combination of them. Yeah, but the simplest possible way is just show every carbon implied by the line segment, and then you don't have to show any H's either. Yep. Okay, any other questions about this? Okay, cool. So getting back to an earlier question is, can we have the carbons linked together in a ring in a way that's not aromatic? And yes, and we can use skeletal structures for that too. So in a non-aromatic, or in other words, in an aliphatic ring. So for example, if we have, maybe let's do a 5-membered ring, because that's the one I drew in my notes. Okay, so 5 carbons all linked into a ring, each with the 2 hydrogens they need to have the full octet going on. We can redraw as just a pentagon if we're doing skeletal structures. Okay, so as kind of a side note here, these alkanes, these are called cycloalkanes. And this one, because it's got 5 carbons, this one happens to be cyclopentane. So they're named after whatever has the same number of carbons, just their cyclo at the front. Okay, so we'll see a little bit more about how to name stuff in just a minute or two. Okay. So before we go on to that, we're going to take a minute and just look at one more thing to do with molecular formula that's kind of interesting and useful for lab this week. And that is degrees of unsaturation. Okay. So you may have noticed that everything in this table is following a pattern. Basically, it's this whole string of like carbon with 2 H's on it. So like a string of methylene units, and then the ends of the chain are capped off with a couple extra hydrogens. So for any number of carbons we have in an alkane like this, so alkanes have a formula of CN, N is just how many carbons there are, and then H, there's going to be 2 H's for every carbon, so H2N, because that's a bunch of methylene units in a chain, and then there's an extra 2 H's to cap off the 2 ends of the chain. So H2N plus 2 is the formula for just like a linear alkane. Okay, so there are ways that we could be short some H's from this formula. For instance, if we join the ends into a ring, or if we do some other stuff to the structure. So alkanes have formula CnH2n plus 2, but every pair of missing H's is called 1 degree of unsaturation. Okay, so the ways to get a degree of unsaturation in the formula is each ring or each pi bond. Causes 1 degree of unsaturation. There's a bunch of different abbreviations for degrees of unsaturation. I think the lab book uses a big omega. I tend to just abbreviate it as deg unsat because it's easier to remember what that means. Okay. So remember that when we've got multiple bonds between atoms, the first bond is always a sigma type bond and all the subsequent bonds are pi. Okay, so a few quick examples here. And these are all just for hydrocarbons. So this one has 0 rings, 0 pi bonds. So this is 0 degrees unsaturation. So with 1, 2, 3, 4, 5, 6 carbons, C6, how many H's would we expect to see here? 14, nice. C6, H, 2n plus 2 is 14. So we don't actually have to go through and draw all the H's explicitly and then count them. We can just look at that, count how many rings and pi bonds there are. There's 0. So if we got 6 carbons, we're expecting 14 H's. Something with some pi bonds in it. All right, so we've got these double bonds here. So we've got 2 pi bonds. So this is 1 sigma 1 pi. This is also 1 sigma 1 pi. So 2 pi bonds and no rings means 2 degrees unsaturation. So again, 6 carbons, C6, H, what? 10, yep. So each degree of unsaturation is 1 pair of missing H's. So we're missing 4 total out of what we should have at a maximum. All right, so that's actually kind of a good side note of where the term degrees of unsaturation comes from. Like a saturated molecule, like this alkane over here, is holding as many H's as it can possibly squeeze in there. It's totally saturated with them. And every pair of missing H's means that it's like not completely saturated with the H's. There's room for more. Okay, I'm going to take just a minute and erase the board real quick over here. So I'm going to not go through the last two examples that I have in the notes, just in the interest of getting through the material for today in time. But the next topic that I wanted to cover is functional groups. And again, if you're taking lab, you've seen a little bit of these already just in the last couple of weeks. So functional groups are like small groups of atoms that behave in a particular characteristic way, usually with not a whole lot of regard for what the rest of the molecule looks like. For example, all alcohol molecules have an OH group attached to them, a hydroxyl group on them. So for example, this is an alcohol, so is this, so is this. And so really, all of these have their OH groups that are going to behave in a pretty similar way. So we have a chapter that's devoted just to reactions of alcohols. So to summarize like what the rest of the molecule looks like, because often it's not that important, we're going to use ROH, where R just means rest of the molecule. Yep. So the one thing that might get its own abbreviation, depending on what we're looking at, is aromatic rings. These actually do react differently from alcohols. And so that might include things like this, basically anything with this six-membered double and single bond pattern. So these, confusingly, get abbreviated as capital A lowercase r, which is also pronounced R, OH, which is a subset of like the capital R, ROH. Okay. So the functional groups that we're going to be seeing a lot of, there's a table of them in the, I think, inside front cover of Loudon. And if you're taking lab, this is actually exactly the same list that I drew for the lab books. But so I've covered alkanes, alkenes, alkynes, and aromatics. But we are going to see some other functional groups in OChem. These are going to be the most common ones. So this CO double bond is going to come up a lot. This is called a carbonyl. So carbon YL. And it's a part of a whole lot of functional groups. So it's part of carboxylic acids, which are carbonyl OH. And it's part of acid chlorides. I guess if I want, I can draw R for rest of the molecule, or I can just leave it like a bond disappearing off to nowhere to be kind of vague. There's a few more on this list. I'm going to sort of skip ahead a little bit, but this one where it's just got an R group on either side of the carbonyl is a ketone. This one is an aldehyde, where it's got an R on one side and an H on the other. Okay, so carbonyls are going to show up in a bunch of stuff. And then we are going to see some other functional groups as well. So R attached to a nitrogen with some number of H's on it. or maybe it's a nitrogen with 2 R groups, or nitrogen with 3 R groups. These are all amines. We're also going to see alcohols, ROH, ethers are ROR, so 2 carbon groups stick together on either side of an oxygen. And then we're going to see what gets abbreviated as RX. X is used as the abbreviation for a halogen. So like F, Cl, Br, or I. If you remember when I drew up that like abbreviated periodic table, that was the one where I bothered to draw the column all the way down, or most of the way down, because this is kind of a useful set of things to look at. These are alkyl halides. Okay, so we're going to show a bunch of ways to make all of these functional groups and then things we can do with them afterwards. Okay, that's a good place to stop for now.